So in rotational motion, I hope you remember the formula, the concept of what? Concept of center of mass, motion of center of mass, velocity of center of mass, acceleration of center of mass, and then angular momentum of a particle, angular momentum of a system of particles, angular momentum of rigid body, then torque due to a force. All these concepts I'll remind you, but our aim for today's class is to solve numerical problems on rotational mechanics. So let us start the revision of the formula, the concept little bit, but all the concept if I tell you, then it will be theory class only. I'll just remind you the formula and little bit concept of rotational mechanics before we start textbook based problem and some problems taken from other books. The concept of rotational mechanics actually starts with the concept of cross product of two vectors. Hope you remember. I'll just remind you the cross product of two vectors, and this is importance in rotational mechanics because not only sums to understand moment of force, angular momentum, we need the concept of cross product of two vectors. So just basic concept I remind you. The cross product between two vectors A and B cross product of vectors A and B is A cross B equal to AB sin theta n cap. This n cap is the unit vector perpendicular to the plane of vector A and vector B. So it is better to say A cross B itself directed along n cap, or A cross B is perpendicular to the plane containing A and B. And A cross B, we have seen that if two vectors are of this form, A1i, A2j, A3k, and B equal to B1i, B2j, B3k, then A cross B we can write in the form of determinant ijk, and then A1, A2, A3, B1, B2, B3. And this on simplification will give you A3, B2 I cap minus A1, B3, A3, B1 J cap plus A1, B2, A2, B1 K cap. Okay. So let me apply this concept in solving a textbook type of problem. Not textbook type of problem, this problem actually NCERT problem. If you go through, I have the old book with me right now. If you go through this sum, NCERT In my book it is page 178, Rotational Mechanics 7.6. Question is, find the components along x, y, z of angular momentum I of a particle. I will definitely explain what is angular momentum. I will definitely remind you what is angular momentum. But we have to solve this sum. Component along x, y, z, angular momentum I of a particle whose position vector is r, with component x, y, z. So I am restating the problem in this manner. Let position vector of a particle, I am writing in my version, not textbook version. Position vector of a particle is given by r equal to this thing, xi plus yj plus zk, and momentum vector given p. P they have not given, but components are given, so p vector also you can write pxi, pyj, pzk, so that if the particle moves only in the xy plane, the angular momentum has only a z component. Before we solve the problem, we need to remember the angular momentum of single particle. It is L equal to r cross p for a particle. L equal to r cross p. For a system of particles, L equal to sigma li, this is sigma ri cross pi. Okay, this is total angular momentum of system of particle. And then for a rigid body, L equal to I omega, isn't it? So this is for one particle only, so we will be using this formula, L equal to r cross p. They have asked you to prove that, you are required to prove that if the particle moves on xy plane, then its angular momentum is directed along z axis. How to prove this? We start this manner. We have L equal to r cross p. So you just write with the help of determinant I, j, k. If you don't know determinant, no problem. You know cross product, you remember that and use it. X, y, z, and this L we write in the form Lxi, Lyj, Lzk. We are writing this way. Okay. So we will compare these two, but let us evaluate the right hand side. I cap ypz minus j cap xpz minus zpx I remember it better with the help of determinant, that's why I am doing. No need to do it for you by determinant. If you know it, you apply it. Otherwise, just write this formula directly. And this will be xpy minus ypx. Whatever you can do, I'll be talking to you after. Ypx. Okay. Now this L has two components, three components, Lxi, Lyj, Lzk. So comparing two sides, we get Lz equal to xpy minus ypx. See, if we compare, then xy plane, that angular momentum will be related to this component only along z axis. That's why this question arises. Okay. If particle moves only in the xy plane only, all these things will rise. That x, y, the angular momentum, linear momentum along x-axis, linear momentum along y-axis, and then you compare. But this is directed in what direction? That will be along z-axis. And this is indeed true. It follows from definition also that if this is your xy plane, this vector is r and this one is p, then L equal to r cross p perpendicular to plane of r and p. It will go this way. Okay. R cross p is perpendicular to the plane of r and p. And if this is in xy plane, say this is your xy plane, then by the concept of cross product, this L vector will be directed along z axis. That's why the question arises. Now, let us remember the concept of torque, because you are doing dot product, cross product, so we need to remember the torque also. Torque I just show you and then we'll be using formula. Torque, there is a object, on it a force is acting, force is acting at the point P. The moment of the force or torque, tau, is defined as what? It is defined as product of force and perpendicular distance. This perpendicular distance. This is r. OM will be r sin theta. So tau will be f r sin theta. Torque vector, if you want to write, then tau will be equal to r cross f. This torque will be clockwise or anti-clockwise. If we imagine that this force acting on this is called lever arm. What is the concept? Imagine the force is acting on this lever arm. If it rotates lever arm in anti-clockwise sense, then the torque will be anti-clockwise. If it rotates in clockwise sense, then it is clockwise torque. This time, if we imagine that force, instead of acting at the point P, acting on this lever arm, then lever arm rotates in what sense? Anti-clockwise sense. So that torque will be anti-clockwise. So in this diagram, in figure, tau is anti-clockwise. Okay, the torque tau is anti-clockwise here, because this force will rotate the lever arm in anti-clockwise sense. That's why it is anti-clockwise. But if it rotates in clockwise sense, then it will be clockwise torque. This torque for system of particle for rigid body also can be defined. For a system of, this is for single force. For many forces acting, net torque will be tau net will be what? This is sigma Ri cross Fi. Okay. I equal to 1 to n. This is for a system of particles. And for a rigid body, tau will be equal to I alpha. Okay. And a rigid body in rotational equilibrium, a rigid body will be in rotational equilibrium if net torque on it 0. Net torque on it equal to 0. That is tau clockwise. If you take positive all the torques clockwise, then if it is positive quantity, anti-clockwise torque will be negative quantity. Tau clockwise minus tau anti-clockwise will be 0. That is tau clockwise will be equal to tau anti-clockwise. Clear? So net torque 0 or net clockwise torque equal to net anti-clockwise torque. This is for equilibrium. So now we are going to work on it. I just, before we start the textbook type of sums, I just ask you one question, one very simple question. A pendulum bob is there. Mass of the bob is m and length of the cord is L. This mass is m. It is taken at a height. It is taken at some height in such a manner that the cord makes an angle theta. The same mass is taken over there. This cord is divided by an angle theta. At this position, find the torque due to the weight. Okay? Till 7:30, whatever you can do, you do. After that, I will interact with you. Find the torque due to the weight. So, this weight mg will be acting downward. The concept of lever arm, I remind you, lever arm, why it was drawn? Just a line of action of the force produced backward, and from the point about which moment is being taken, we have drawn this perpendicular. This length of perpendicular into force will give you torque. That's why. Why? That OM equal to R sin theta. So torque we have defined F into OM. OM you put, it will be F into R sin theta. Clear? So in this case we have to find the lever arm. How? We produce the line of action of the force in backward direction. Now draw a perpendicular. This is our example 1 on torque. So lever arm you have identified, line of action, and from the point of suspension you have drawn a perpendicular. Then this length of perpendicular, I mean length of lever arm is equal to what? This is theta, means this one also theta. So this is L sin theta. So tau is going to be mg into L sin theta. This is just mgl sin theta. This is torque of the force. Force into perpendicular distance. Let us solve another question here. For better understanding, we will be doing this. I am just drawing an object where a point O is there, a force acting on the object this manner, this force F is equal to 3 Newton, another force acting whose magnitude is 5 Newton, and this 3 Newton is at a distance, say 5 centimeter from here, and this one situated at a distance 4 centimeter from the point O. Question is, find the net moment of force. How to find it? Net moment of force. This is OL, one lever arm, one perpendicular. OM is another perpendicular. 3 Newton force acting on the object, but when you draw perpendicular, we will imagine that it is acting on this perpendicular only. So torque due to force F equal to 3 Newton about O will be 3 into OL, and it rotates OL in anti-clockwise sense. So this will be anti-clockwise torque. 3 into 5, 15 Newton centimeter. This is anti-clockwise. And this one, this 5 Newton. Now let us calculate torque due to torque due to 5 Newton force about O. This is also 5 into 4, but it will rotate this lever arm in what sense? Clockwise or anti-clockwise? This is also anti-clockwise sense. So 5 into 4, 20 Newton centimeter. This is also anti-clockwise. So net torque will be added. Tau 1 plus tau 2 35 by 100 Newton meter, which is nothing but 0.35 Newton meter. But if by chance 5 newtons say acting this manner, then it will be subtracted from there. Just keep the concept in your mind. So what is the learning from here? That torque due to single force, torque due to many forces. Torque due to rigid body we have not done yet, we will be doing it definitely. Wait. And another thing I told you, for equilibrium, net clockwise torque will be equal to net anticlockwise. If suppose you want to keep this rod whose weight is say 5 kilogram, and two weights of different masses are acting. This is 10 kg and this is say 30 kg at the ends. Can you keep it in equilibrium? You can't. But if you put another support here at this point, then there is a chance. This is your common sense without knowing physics. Why? Because about this point torque of 30 kg will be more than torque of 10 kg. So it has tendency of rotation in clockwise sense. To stop moving that way, we need a pivot at this point. If we keep a pivot here there, then we can keep the rod in equilibrium. Okay, it will not rotate. It will be fixed. If you pivot it at the midpoint, normally just for a rod, no weight suspended. This is the rod. To keep it in equilibrium, pivot will be here. But in this problem, pivot you have to keep at some point like this, not at the midpoint. Then it will not be in equilibrium because unequal weights are acting over there. Okay? So before we apply textbook sum, I remind you the concept of moment of inertia also. In theory class I have done in details. This rigid body is say rotating, constituted of masses m1, m2, mn, rotating with angular velocity omega. Then total kinetic energy is given by half m1 v1 square. We have simplified it. I am not doing the simplification, just writing mn vn square. In this class only we have proved that it is half I omega square. And you can check the formula. I is sigma mi ri square, the moment of inertia. This is called moment of inertia. Total kinetic energy is half pi omega square. I is the moment of inertia. It plays the same role as that of mass in Newtonian mechanics. Now, one term probably I forgot to tell you in theory class, that is called radius of gyration. What is that? Radius of gyration we normally denote by the letter K. We denote this by the letter K. What is that? Instead of this total mass m equal to sigma mi, if we keep a single mass m at a distance k from axis of rotation, then moment of inertia of this mass will be what? Mk square. Single mass moment of inertia, mass into distance square. But for this system of particles or whatever rigid body also, I equal to what? I equal to mk square. I is sigma mi ri square. Okay. So for point mass, whose mass is equal to mass of the rigid body, it is mk square, and for system of particles, it is mi ri square. So if we make these two things equal, then the value of k will be radius of gyration. If we put mk square equal to sigma mi square, then k equal to under root this is called radius of gyration. Okay, we denote this by the letter k equal to under root sigma mi square by total mass m. Let me apply it in one sum. Moment of inertia formula, I think you remember those standard moment of inertia formula. Mi of a solid uniform rod if it rotates about an axis passing through one of its end, then I equal to what? 1/3 ml square. Remember this? For a solid sphere, if this one is a solid sphere of mass m, radius r, this is for a rod. For solid sphere, I equal to 2/5 mr square. It's rotating about its own axis. Then moment of inertia is 2/5 mr square. For a ring, this ring, for this ring, its mass m, radius r, mi equal to, for a ring it is mr square. For a hollow cylinder, it is like this only, like ring only, it is made of rings. So formula will not going to change. This moment of inertia of hollow cylinder of mass m, radius r, this is also m r square. Done for hollow cylinder. For a disc, for a uniform disc, I equal to what? 1/2 mr square. And this is true for a solid cylinder also. For a solid cylinder also, I equal to 1/2 mr square. For this solid cylinder, if it rotates about its axis, then moment of inertia is 1/2 mr square. Because it is made of smaller discs, many discs are there, they will form the cylindrical, solid cylindrical object. So moment of inertia of that is equal to moment of inertia of solid cylinder 1/2 mr square. The way for ring and for hollow ring. Clear? Only keep this formula in mind. NCERT has reduced the syllabus in much. Today's class will be discussing on it. Okay, Just do one problem on radius of gyration. Just I told you, find the radius of gyration of a disc uniform mass m and radius equal to r. Find the radius of gyration of a disc of mass m and radius r rotating about its own axis. How to find it? I remind you the method. This is the disc. This disc is solid uniform disc. This is rotating about the axis xy. Its moment of inertia, you know, that is I equal to what? Half m r square. It has mass m and radius r. Now what I am doing there, I am replacing this disc by single particle of mass m at a distance k. Then what will be the moment of inertia of this single mass? mk square. You agree? Mass into distance is square. Now put half m r square equal to mk square. So k equal to r by 2. The value of radius of gyration is going to be r by root 2. You can find radius of gyration in any problem if you remember the simple concept. We replace the whole mass by a single mass. Moment of inertia of the rigid body or disc, whatever you have taken, that matches with moment of inertia of the single mass, then the distance where you place the single mass, that is called radius of gyration. Okay, clear? So we found radius of gyration in this case r by root 2, k equal to r by 2. If a sphere is there rotating about its own axis, how to find radius of gyration? For a sphere, this we did for a disc. A sphere rotating about its own axis. For a sphere, see, very simple now. This is the sphere. It has its axis of rotation, a diameter, rotating. What will be the radius of gyration for this sphere? Its mass is m and radius is r. How do you find it? The same manner, what is its moment of inertia? I equal to 2 by 5 mr square. Now keep a single mass m at a distance k from the axis of rotation. Okay. Now mk square equal to 2 by 5 m r square. Okay. So k will be r root 2 by 5. Found? Irreducibility at this distance, if you keep the mass, whose mass is equal to sphere, then moment of inertia of the sphere and this point mass will have the same value. Clear? Now let us go for solving some textbook problems. Another thing I have to remind you, better to say, that for rigid body, obviously you have revised properly and then doing it here with me, no problem, no issue. But based on the concept so far we have done, that is equation of motion of rigid bodies, we haven't done. This is better to say rotational equation of motion of rigid bodies. Okay. What are those? That is initial angular velocity with which it starts rotating omega 0, angular acceleration alpha, after time t angular velocity will be omega 0 plus alpha t. Then second one, like a is equal to ut plus half at square, you know, theta equal to ut. Number 2. And the third one is understood? These three enough. Okay. So if they ask you to giving that angular acceleration, if they ask you to find angular velocity after 5 seconds, you just use equation 1. If they have asked you how much it is rotated, rigid body subjected to this torque, angular acceleration this much produced, then how to find what angle is formed after certain time? That can be done by formula 2. Angular velocity can be determined by this formula 3. Okay. So these equations and concept of torque, angular momentum, all these we are going to apply these textbook problems. Torques of, read the sum, torques of equal magnitude applied to a hollow cylinder and a solid sphere, both having same mass and radius. Cylinder is free to rotate about its standard axis of symmetry. Sphere is free to rotate about an axis passing through its center. Which of the two will acquire greater angular speeds after a given time? Torques of equal magnitude applied. Torque formula, you know, tau equal to I into alpha, and for single particle you have defined R cross F. We are just doing it. Now this is an NCERT problem. Maybe this number is changed. This in my book. Wait a minute, I'll just check it. 7.11 in the old book. Torque with tau applied on a hollow cylinder and a solid sphere. Hollow cylinder, I equal to, so many problems, try all. I equal to half m r square, moment of inertia. Hollow cylinder, I on calculation, sorry, oh my god, wait. I want to write tau. Tau is I alpha sigma mi ri square. This is I. So torque, this tau we have applied on hollow cylinder. So tau 1 will be I1 into alpha, tau 2 equal to I2 into alpha. If you can't, then better you pay attention here. Okay. I1 alpha 1 and this is I2 into alpha 2. Same mass and radius. So you write, this is for what? This is for hollow cylinder. And this is for solid sphere. For hollow cylinder, I1 will be half mr square. This I2 will be 2 by 5 mr square. Do one of the thing, either this or that. Cannot waste your time here. So angular acceleration here produced by alpha 1 and here it will be alpha 2. So tau has same value. This question is given in NCERT question number 7.11, rigid body mechanics. I mean system of particles and rotational motion. And same tau 1 equal to tau 2. So tau I1 alpha 1, you put it there. This implies the value of I1 half m r square alpha 1 and this is m r square alpha 2. So alpha 1 is 4 by 5 alpha 2. This is your number 1. Now they have given which one acquire a greater angular speed. What is the formula for angular speed? The formula for angular speed is omega equal to omega 0 plus alpha t. They are starting from rest. So omega 0 will be 0. Omega will be alpha t only. So now write omega 1 for hollow cylinder. It's alpha 1 into t. Omega sphere will be alpha 2 into t. So omega cylinder by omega sphere will be 4 by 5 less than 1. So omega c will be less than omega s. Angular velocity of cylinder will be less than angular velocity of the sphere. Understood? We are just writing equations of motion and the formula for rotational mechanics, whatever we have learned. Okay, go for next one. A rope of negligible mass is This is in my book 7.14. New edition, it may be changed. Just check. Rope of negligible mass is wound round a hollow cylinder of mass 3 kg and radius 40 cm. What is the angular acceleration of the cylinder if the rope is pulled with a force of 30 Newton? Cylinder you can imagine it's like this, lying on horizontal surface and a rope is attached to it. This rope is being used to hollow cylinder given its moment of inertia, you know, I equal to just m r square, m into r square. So if you just imagine the surface of the cylinder, it's like this. This cord wound over this cylinder. It means if only this force is acting, then the cylinder has tendency of rotation. It starts rotating. Cylinder has tendency of rotation. Why? Because on the cylinder, if you keep it this manner, then also if you give any tangential force, then it starts rotating. Force applied tangentially, then it starts rotating. If we keep a cylinder in our hand and then apply torque here, force here, then it starts rotating. So if 30 Newton applied means it will start rotating, and moment of the force will be what? If the force applied be F, then moment of the force will be, for this case of cylinder, tau will be equal to F into R. F is 30 Newton, 0.4, so this is 12 Newton meter, tau equal to. Okay. Now put tau equal to I alpha. So alpha equal to tau by I. I you write, mass is 3 into 0.4 square. 3 into 0.16. I is 0.48 and tau is F into R. F into R is what? F 30 Newton, and tau will be equal to this tangential force you have applied into radius. Okay, so that force 30 Newton into radius. What is the radius? 0.4 meter. Oh, tau I have calculated here, sorry. Tau is done before, that is 12 Newton meter. So put it there now to get alpha. 12 by 0.48. You can now simplify it easily. It's 12, 4, 25. 25 rad per second square, because we have taken all SI units. Clear? Understood? 30 Newton force you have given. So for that alpha will be this. Angular acceleration. Linear acceleration will be what? The formula for this chord. This is angular acceleration of cylinder, alpha. But chord with that you are pulling the cylinder tangentially, no? That acceleration will be what? R into alpha. So linear acceleration A equal to R alpha, just put the value. R is what? And alpha is 25. This is 10. This is 10 meter per second square. Clear? Understood? Go for next one. A child stands at center of turntable with two arms. This is 7.13 from NCERT. Two arms outstretched. Turntable is set rotating with angular speed 40 revolution per minute. How much is the angular speed of the child? Do the first part first. Okay. Turntable is set rotating with an angular speed 40 revolution per minute. How much is the angular speed of child if he folds his hand back and thereby reduces moment of inertia, because when it stretches the hands, then mass into distance is square. Moment of inertia definition you know. So mass into distance square increases. I increases. I mean I is there, but if he folds his hands, then masses are not spread out from the axis of rotation, so it will be reduced. So how do you solve that case? You can use the concept of no external torque acting in for this problem. No external torque acts. This implies tau external equal to 0. This implies tau external is what? This we did in theory class, d dt of L or d dt of I omega. d dt of L equal to 0. This implies L equal to a constant. That is I omega equal to a constant. I1 omega 1, I2 omega 2, like this. Okay? I into omega a constant, these two are equal. I1 omega 1 equal to I2 omega 2 in absence of external, because the child himself or herself folding hand, no external torque is responsible for it. That's why I1 omega 1, I2 omega 2, these two will be equal. I1 initially what? That is I1 say, initial one. I2 will be what? It is given by folding hand, reducing the moment of inertia. It will be 2 by 5 I1. Okay? What is initial angular speed? 40 rev per minute. Your problem is to find omega 2. Very simple. Just put I1 omega 1 equal to I2 omega 2. Just do it. By using this you can find it easily. You can find it very fast. Okay? So put I2 equal to 2 by 5 I1. I1 into 40 so W2 will be 100 revolution per minute. Clear? Go for next one. State the child's new kinetic energy of rotation is more than initial kinetic energy of rotation. How do I account for increase in kinetic energy? Very easy. Rotational kinetic energy of rigid body formula, we can use it here. Okay? So what is initial rotational kinetic energy? EI half I omega square, and EF I2 omega 2 square. Okay? Now EF by EI half I2 omega 2 square, that divided by half I1 omega 1 square. You know omega 1 omega 2 ratio? Omega 1 is 40, put it there. So I1 I2, this ratio also you got. I2 by I1 is 2 by 5. 2 by 5, 100 square by 40 square. So 2 by 5 this is becoming 5 by 2 whole square. It's coming 5 by 2 only. It is greater than 1. So if final is greater than EI, isn't it? Final kinetic energy is greater than the initial kinetic energy. Then they have asked you to find how to account for increase in kinetic energy. Very easy, increase in kinetic energy. Because EF you got, EF is how much? 5 by 2 EI. Therefore, delta E, change of kinetic energy EF minus EI. This is 3 by 2 into EI. How do we account EI? Initial kinetic energy. See, angular speed is given, but moment of inertia is not given. So we cannot find it exclusively. Formula is this. It is 3 by 2 into EI. But EI exact value we don't know. We have compared, it's fine, but we don't know its exact value. Half I into omega square. You will put it there. Whatever you get, if the data given, then you will do. Now this problem, you all can see this. Meter stick balanced on a knife edge at the center. When two coins each of mass 5 gram are put on the top of the other, the stick is found to be balanced at 45 centimeters. This is a meter stick, midpoint. Mass of the meter stick, first you consider this situation, meter stick is AB, put on the top of other 12 centimeter mark. Mark is starting from here. Say this mark is 12. Two coins are placed one above the other. Their load is acting downward. That is 10G. 5G plus 5G. Stick is found to be balanced at 45. This is 45. What is the mass of the meter stick? Meter stick mass will act through which point? This will act through its center of mass. Okay? So that will act through this point whose distance from this end equal to 50 centimeter. Weight of the meter stick be W, acting this way. Question is, today I am starting this sum, but finally I will be meeting with you again in another session. I will be discussing next type, other types of sum. Just listen this one. This W equal to mg is the load you have to find. Hinge is kept at 45. How will you find it? If this one has reaction in upward direction R, then R you can write 10G plus mg. But it doesn't give us neither mg nor R. Then what to do? The easiest method is to find torque. Moment of this torque about the point P equal to moment of this load of 10 kg, 10 gram about this point. This is the answer. Okay? So this distance is how much? 5 centimeter only. This is 45, this is 5. Now this torque will be clockwise because this lever arm rotates in clockwise sense. Tau 1 equal to mg into 5, and torque due to this 10 gram will be what? Tell it is 10G into this distance. This is 12 centimeter. This is 33 centimeter. Now for equilibrium, you just put tau 1 equal to tau 2. Therefore, so you can find mg from here. Just cancel 2g into 66g. Clear? So weight of this will be 66g. Weight of what? Weight of the rod. Okay. So you practice the remaining sums as many as possible, then ask your doubts. Next session I will be discussing